Bismillahirrahmanirrahim. I am Dr. Muhammad Adnan, working as Assistant Professor in the Department of Physics, Kohat University of Science and Technology. I welcome you to the course PHY 352 Nuclear Physics 1. Today it is the 17th lecture of this course and the topic is nuclear excited states. First, I will give the learning objectives. At the end of this lecture, the student will know the concept of nuclear energy levels and excited states. In this course, we are following the book Introductory Nuclear Physics by Kenneth S. Crane, 3rd edition. In this lecture, I have taken some of the illustrations from this book. Before we start with the nuclear energy level and excited state, we need to review for your understanding the energy levels of an atom. So you already know from your atomic physics course that electrons that revolve around the nucleus move in a fairly well-defined orbits or energy states. Now, some of these electrons are more tightly bound in atoms than others. For example, only 7.38 electron volts is required to remove the outermost electron from the lead atom, while 88,000 electron volt is required to remove the innermost electrons. So from this the statement that some of the electrons inside the atom are tightly bound, which require more energy as compared to the electrons which are loosely bound to the atom. Those electrons are the outermost and the tightly bound electrons are innermost electrons, which require huge energy to remove it from the atoms. So you all know this concept, and based on this description, you know that the process of removing electron from an atom is called the ionization, and the energy required to remove electrons from the atoms are known as the ionization energy. Now, in a neutral atom having Z number of electrons, it is possible for the electrons to be in a variety of different orbits, each with a different energy level. As here we have discussed that inside the atom, electrons are revolving around the nucleus in well-defined orbit. So in an atom having Z electron, these electrons, it is possible for these electrons to be in a variety of different energy orbits with different energy levels. Now, the state of lowest energy is the one in which atom is normally found and is called the ground state. So, as I told you before, moving into the nuclear energy level and excited state, we need to use the same concept of the atomic physics. So the lowest energy state of an atom is known as the ground state. With the atom, when the atom possesses more energy than its ground state, it is said to be in an excited state. So you see, you know the concept of ground state and excited state from your atomic physics. So we'll be using the same things in nuclear physics while working with topics nuclear excited states. Now, a few other realities that you know from the atomic physics, that an atom cannot stay in the excited state for an indefinite period of time, but rather an excited atom will either eventually transfer to the lowest energy excited state or directly to the ground state, as you have done in atomic physics course, the various atomic transitions that give rise to some electromagnetic energies. That is, while doing so, that is when an atom inside an atom, electron make transition between these orbits, whether it eventually going towards the ground state or the lowest energy state. This is performed by emitting a discrete bundle of electromagnetic energy called photons. And the highest energy or the most energetic photons that an atom can give off by the electronic transition, or we can say the inner shell transition, are known as the X-rays. So the energy of these photons will be equal to the difference between the energy levels of the atom. That is, through which the transitions occur, the difference of the energy will be emitted in the form of these electromagnetic energy known as photons. Now, the same thing that we'll be using for the nuclear energy levels and in the excited state. So based on those descriptions that we have discussed on the previous slide regarding the atomic levels, or we can say the energy level of an atom, here we will be discussing the energy levels of a nucleus. Now, the nucleons in the nucleus of an atom, like the electron that revolve around the nucleus, exist in shell that corresponds to the energy state. So like the electrons, nucleons inside the nucleus also exist, or we can say they have different energy states in which they are they have different definite energies. But the difference between the energy levels of a nucleus and energy level of an atom is that nucleons have no center to orbit around it, as will be clarified after the shell model. But you know that the energy levels of an atom, the electrons are orbiting the nucleus in well-defined orbits, as we have discussed, but in the nucleus, nucleons have no center to orbit around it, but they are moving under the average central potential that we will be discussing in the shell model part. Now, the energy shells of the nucleons in the nucleus are less defined and less understood than those of the electrons of the atoms. So in this course you will be discussing those nuclear energy levels once we are done with the shell model. There is a state of lowest energy, the ground state, and discrete possible excited states of the nucleus, as we have discussed in a similar way of the atomic energy level. So nucleus also have the concept of ground state and also the excited state. So where the discrete energy states for the electrons of an atom are measured in electron volt or keV volt, that is the difference of the energies. Once we are talking about atomic physics, they are of the order of kV. The energy levels of the nucleus are considerably greater and typically measured in MeV. So the photon emitted by the nucleons transitions are known as the gamma rays, and which are more energetic than the highest energy photon emitted by the atom. As we have discussed, those are X-rays, and the photon emitted by the nucleus are known as the gamma rays. So gamma rays are having more energy than the X-rays. Now, a nucleus that is in the excited state will not remain at that energy level for an indefinite period, as we have discussed with regard the atomic energy levels. So, like the electron in the excited atom, nucleons in the excited nucleus will make a transition towards the lowest energy configuration, and in doing so emit a discrete bundle of electromagnetic radiation called a gamma rays, as I have told you in terms of the energies. Now, the only difference between the X-rays and gamma rays are their energy levels. That is, these are kilo electron volt, and these are measured in mega electron volt, their energy level, and whether they are emitted from the electron shell or from the nucleus. So as I told you on the previous slide, that gamma rays are emitted due to the nucleonic transition, and this is the atomic transition from the inner shell of the electrons. So this is the only difference in terms of the energy and also in terms of their origin. So how one can describe these nuclear energy levels and the excited states? So the ground state and the excited states of a nucleus can be depicted in a nuclear energy diagram, nuclear energy level diagram, as we have taken this energy level diagram for the nickel 60. So here you have this is the ground state, and these are the various excited state. The energies are there. These transition will give rise to these gamma rays having that particular energy, which is equal to the difference of the two states. So the nuclear energy level diagram consists of a stack of horizontal bars, as I told you, one bar for each of the excited states of the nucleus. These are the various excited states. The vertical distance between the bar representing the excited state and the bar representing the ground state proportional to the energy level of the excited state with respect to the ground state. As I told you, for example, this one is 1.332 mega electron volt. So the photon emitted, if the transition occur between this level to the ground state, so it will emit the energy equal to 1.332 mega electron volt. Similarly with all these numbers. The difference in the energy between the ground state and the excited state is called the excitation energy, the same concept of the atomic physics. The ground state of a nuclei in this case has zero excited energy. The bars for the excited states are labeled with their respective energy, as we have discussed. So you can just describe this nuclear energy level diagram based on these descriptions. So if we just conclude what we have done, so we have learned that just about the atoms by studying the excited state, we study the nuclear structure in part through the properties of a nuclear excited state. And like atomic excited state, the nuclear excited states are unstable and decay rapidly to the ground state. Now in atom, we make excited state by moving individual electrons to the higher energy orbits, and we can do the same for individual nucleons. So we can say that the excited states can reveal something about the orbits of individual nucleons. As I told you, just like in atom, we make excited states by moving individual electron to higher energy orbit. So in the same way, individual nucleons, and thus the excited states can reveal something about the orbits of the individual nucleons. We have already several times in this course referred to the complementary single particle and collective structures of the nuclei. If you remember the various concept that we have discussed in the last few lectures, the intrinsic spin, the parity, and all those things. So one can also produce excited state by adding energy to the core of paired electron. If you remember, in my last lecture, we have discussed the concept of parity, the quadrupole moments, and the magnetic moments. So those are described in terms of the pair nucleons and valence nucleons. So here the thing is that we can also produce excited state by adding energy to the core of paired nucleons, as we have discussed that paired nucleons give rise to in some situation give rise to very large electric quadrupole moments of a nuclei. So in that regard, sometimes these paired nucleons take part in various aspects that we have discussed. So in the same way, if one give energy to the nuclei so that excitation can be produced with the paired nucleons rather than with only the unpaired or the valence electrons, nucleons. Now, by adding energy to the nuclei, that energy can take the form of collective rotation or vibration of the entire core. That is, the core part of the nucleus is that part which is uniformly dense and it might even break one of the pairs, as we have discussed, thereby adding two additional valence nucleons. That is, the pair then give rise to some nucleons in the valence energy levels. That is, one can produce the excitations in the paired nucleons. Now, part of the goal of nuclear spectroscopy is to observe the possible excited state and to measure their properties. For example, the experimental techniques available include all manner of radioactive decay and the nuclear reaction studies that will be considered in details in the remaining course once we are done with the nuclear models. We will be just describing theoretically, but if someone is interested in the experimental aspects of measuring the various the properties that we have discussed in the last few lectures, and also describing these various excited states of the nucleus, so for that you need to refer your Crane book beyond chapter number 16. Now, among the properties we should like to measure for each excited state are, as I told you, energy of excitation, lifetime and modes of decay, the spin and parity, the magnetic dipole moment, and the electric quadrupole moments. So, with more than 1,000 individual nuclei, each of which may have hundreds of excited states, as we have discussed one of the nuclear energy level diagram on the next slide. Again, we'll be describing a few diagrams. So they may have these individual nuclei may have several hundreds of excited states. Now the task of measuring, tabulating and interpreting these data are almost overwhelming. For example, we have some energy level scheme showing the excited state that is below the 2 mega electron volt energy. Now these are various elements, and these are the various the ground states and the excited states. So this figure shows some simple nuclear level schemes. Now, a few of the excited states are identified as originating from excitation of the valence nucleons or the core. As we have discussed, one can produce excitation in the paired nucleons, the core, and also some are identified as the valence nucleons. Now, such identification come about only, as I told you, after the properties listed that we have discussed, the decay mode, the parity, the spin, and all those properties that we have discussed have been measured, compared with the prediction of calculation based on either single particle or collective core excitation to see which agrees with the best experiments. So one need to explore experimental techniques used to extract this information and a nuclear model used to interpret it. So that is beyond the level of this course, but we will be discussing this energy diagram regarding the scope of this course. So one only through difficult and precise experiments and through calculation involving the most powerful computer now available can we obtain such detailed interpretations of nuclear structures. But if we just study this energy diagram or the various excited states, so if you remember in my last lecture I told you that this is the representation of any energy level. For example, this is an element AU having 13 proton, 12 neutron, and total 25 nucleons. So for this state, for example, the spin is 1/2 and having even parity. This one is having spin 3/2 and even parity. So all these are having even parity. So similarly, with all these things, you can describe these notation now easily. Now, if you see some nuclei such as BI 209 show great simplicity. For example, these are just a few energy levels which are not splitting, so this is a simplest case. While other such as this one, for example, TA 182 nucleons, this element TA, show great complexity. For example, there is a great complexity associated. For example, between the energy, say between the energy 0.5 mega electron volt to 1 electron volt, there are around 31 energy levels, and also there are more than 50 levels above 1 mega electron volt. So these are the various excited states, and that can be produced either by giving energy to the nucleus. Now here if we see, there is a regularity associated with the levels of O178. For example, this one, there is a regularity. All the states are having again even parity. So now that is the case when all even Z, even N, for example this one, in the range, let's say the nucleon number is in between 150 to, let's say, 190. This A lies in this range and having even Z and even N, so that there will be a regularity associated. So once we are in a position to describe the various models, and particularly the shell model, we'll be able to extract more of the information from these energy level diagrams for a nuclei and the various excited states. So with this, I thank you for your time.